what's a C, what's a P, and why are they getting violated? Someone from the Netherlands is going to ask that question. Why is there a bicycle at the beginning of your experiment? Don't press that button. Don't press that button. Hello, everybody, and welcome to Early Morning Coffee at CERN. My name is Stephen Goldfarb.
And I'm Yasmine Amhis.
Hello, I'm Piotr Koppenburg.
We have two guests here today from the LHCb experiment. You might or might not have heard of the LHCb experiment. You probably might know the acronym LHC, which stands for the Large Hadron Collider. As you might know, the Large Hadron Collider is a very large, round accelerator, which is 27 kilometers around, or to my friends in the US, 17 miles around. It's buried underground about 100 meters, and it has the purpose with its superconducting magnets, thousands of superconducting magnets, to accelerate protons in the counterclockwise and the clockwise direction to make collisions at different points along the ring. There are four places which we affectionately call 1, 2, 5, and 8. And I'm not going to explain exactly why we chose those points. They have the crossing points where we make the beams pass through each other. And yes, I know, in Ghostbusters they tell you not to do that. But in our case, we want to do that because we want to collide the protons and see what comes from them. Two of those points we talked about in a previous edition. If you haven't seen it yet, we had the Higgs boson special where we talked to physicists from the ATLAS and CMS experiments at point 1 and point 5. Now we're going to go to point 8, where is situated the LHCb experiment. So before we get started, maybe Yasmine, you could tell us a little bit about yourself. What brought you to CERN and to LHCb?
So what brought me to LHCb, I guess like a lot of people, I was a summer student 19 years ago. And my project then was already on the LHCb experiment. So after that, I had kind of the traditional path of the PhD, postdoc, all on LHCb. And then I did stick around for all of this time, 19 years.
19 years on LHCb. That's
Yeah.
almost as long as I've been on ATLAS,
Yeah.
actually. That's, well, congratulations.
Thank you very much.
You never thought maybe about, another experiment?
So I did a little bit. I had joined for some amount of time a small neutrino experiment called SOLID. So I joined that one for 3 years or so. But then it was a bit complicated to manage both experiments at kind of full speed.
Yeah.
So I decided to stick to the one.
Okay.
Yeah.
Well, can I ask, before we go on to Patrick, where did you come from originally?
So I come from Algeria. I was born and raised there. And then I moved to France for university and, university, PhD and all of that. And then I spent some time at CERN at EPFL in Lausanne, not so far from here.
Not far from here.
My friend here is from also. And now I'm in an institute. I'll go back to an institute in Paris.
Okay, very good.
After my stay at CERN.
Excellent. Okay, Patrick?
Yeah, so as Yasmine said, I grew up in the area in Lausanne, 50 kilometers away from here, where I studied physics at the university and then started a PhD already on the LHCb experiment. That was in 96. And at the time, the experiment was not even approved yet. And we didn't have any data, but I still did my PhD there. And so after that, I escaped to see some actual real data to Japan to work on the Bell experiment for 2 years. But then I came back as a CERN fellow, where I shared an office with Yasmine for a couple of months. And then to London, Imperial College, and NICEF in Amsterdam. But they sent me here, so I'm mostly here at CERN working on the LHCb experiment for the Dutch community.
Wow. So physicists on LHCb are very fidel to their experiment, I think. You're very fidel to beauty in general, yes. which is what the B stands for. People might wonder, why do you put a B at the end of LHC? LHCb, the B stands for B, which is the B quark. We like to call it the beauty quark. Some people call it the bottom quark. We don't associate with those people. Maybe you could fill us in. Why do we study the B quark?
So the B quark is super interesting because it's one of these quarks that we have. So you have explained this already. We have 6 quarks in the standard model, as far as we know. And the B quark is really cool to help us understand the difference between matter and antimatter. So at the LHC, we have the possibility to produce many of them, many B quarks, many anti-B quarks, and then we see kind of with our measurements how they behave, why they're different, what we can learn from that. So this is why we like them so much.
That's what it's just we can study the difference. So why? I would have thought that every particle has an antiparticle, right? But the B systems with the B quark in it are special and that you can see some sort of imbalance?
Absolutely. So there is a little imbalance, and these imbalances can be quite small. And what's nice with these bees is that we can explore interferences, you know, like the experiments that we can do with light and so on. And with these interferences, we can increase some of these differences if you want. And it's like we can see them better. So this is what makes this bee special. And there are some other particles which have similar properties. But in the case of the bee, it's a little bit easier to access than other quarks, for instance.
Okay. Now, it might be surprising to know that you can access a quark, because quarks, my understanding, and I am a
You're right.
Full
You're
disclosure,
right.
I'm a particle physicist, and I actually studied B hadrons on the L3 experiment when I worked at the University of Lausanne. So full disclosure, I knew Patrick from way back when he was a student and I was a postdoc. I guess what's advantageous at the LHC is we can actually distinguish particles that contain the B quark, hadrons that contain the B quark. A hadron is a particle made up of different quarks, and we can see them because of their slightly longer lifetime.
Absolutely. So the lifetime of a bee is about 1.5 picoseconds. So picoseconds is
That's forever.
That's forever. And we use the fact that when they're created at the LHC, they come with a lot of energy, and we say that they're boosted. And because they're boosted, we benefit from that, such that the lifetime appears to be longer when you are looking at them from the lab. So thanks to this boost, like you say, they have a long lifetime, and we have just more time to study more things about them.
Okay. As opposed to, I don't know, Patrick, there's other particles you study as well. I suppose that the C quark, I've heard, is also being studied?
Yes, we are also doing C quarks at LHCb. Some people like to call us LHCC, but that acronym is already taken by a committee.
Okay.
We have a full program with the C quark and the hadrons containing C quarks, which are called D particles. They also have a reasonably long lifetime. So you can also make a lot of studies, but they're much less sensitive to CP violation effects.
Okay, so let's investigate this CP violation. What's a C, what's a P, and why are they getting violated in the LHC?
All right, so C and P. So C stands for charge and P for parity. So one of the important things that we have in physics are symmetries. We love symmetries. And C and P are what we call discrete symmetries. So they're very interesting because when we combine them and we sort of apply them to a particle, it's a bit abstract to say kind of what does it mean to apply symmetry to a particle. But you have to remember that the way that we describe things is like states, is like this almost mathematical objects, you know? So you can imagine that you apply the symmetries to these particles, and what happens in the case of the particles containing a B quark is that they behave differently under the CP symmetry. And this is why what Patrick was saying is that when we say that there is CP violation, it means that a particle and an antiparticle, whether it's a B or it's a D meson, they will behave differently. And this is what we're trying to study. It's a very important property that we're trying to study.
Why are they different, right? Why are we seeing these things being different? So just to make sure I understand this. So C stands for charge.
Correct.
And if we say it's a symmetry.
Yes.
That means that if I have, let's say, an electron and a positron, and I apply the same magnetic field but differently, the opposites, they'll behave exactly the same. And there's some sort of symmetry between the behavior it doesn't depend on the charge.
That's correct, yeah.
Okay, so there's charge. Sorry, I understand that.
Yep.
Okay. And then there's parity.
Yeah.
So it's a little more complicated. I guess it's like a mirror?
It's like a mirror. You can think about it absolutely like a mirror. And what happens is that, so the particles, you can think of them like they have their anatomy chart and some properties. And one of them is the spin. So you can think of it also as one of these things that will be inverted in this mirror that you're, talking about. So you can also think about it in these terms. But the simplest way, I agree, is to look at parity as like when you're looking at yourself in a mirror.
Look at yourself.
Yeah.
But then we aren't symmetric in parity, right? I think that the human beings, at least, we look like, if you ever take a picture and take the two sides, it's scary, actually.
It's a bit scary.
But now when you take charge and parity together, that tells you something about antimatter.
Absolutely.
There's a difference between matter and antimatter.
Exactly. So the fact that, this behavior is different, it tells you something about matter and antimatter behaving differently. And the reason is that we think that at the start of the universe, we created the same amount during the Big Bang, the same amount of matter and antimatter. Yet, one of them has disappeared. So you are made of matter. This microphone here that I'm talking to is made of matter.
I hope so.
I hope so.
Don't touch it.
And as far as we know, there's almost no antimatter left in the universe. So this is one of the things that we're trying to understand. And what's really cool about the LHC is that we can produce a lot of this antimatter in the laboratory and then have it kind of super handy to understand the difference between matter and antimatter.
It's naturally produced in our collisions, right?
It is produced, yes, in our collisions,
together.
exactly.
We always see equal amounts, but then you can study these slight asymmetries.
Absolutely.
In the B quark. Okay, so I'm starting to understand this a bit. There's a lot of other stuff, though. I've seen a lot of headlines coming out of LHCb. And we have here, Patrick, do you have a copy of the particle data group book? This is our
heavy.
Yeah, if there were a Bible for particle physics, the things that we consider to be true, it's the particle data group book, because it contains all the properties that we've measured of all the different particles, and there's a lot of particles in there now. But now, I don't want anyone to be confused. There's different things called particles. There's elementary particles. When we talk about the quarks, we're talking about elementary particles. You can't break them open anymore. There's nothing inside. This keeps track of not just them and their properties, but all of the different combinations. And amazingly, LHCb has made a lot of entries in that book. Maybe, Patrick, you could comment on all the different. We have a lot of new hadrons, I guess, that have come up from discoveries.
The LHC is known for having found the Higgs boson, but the LHC has also found 75 new particles that are hadrons. So the hadrons, they are the particles made of quarks. There's essentially two families of them. There are those that are made of a quark and an antiquark, and then there are those that are made of three quarks or three antiquarks. We tend to put them together because of CP symmetry. And these are called baryons. But there's nothing that forbids making particles with 4 or 5 or even more quarks. Now, until the LHC switched on, we hadn't found any, or there were a few that were discovered at the Bell experiment while I was there, but we weren't really sure whether they were made of 4 quarks. Now we know that some of them are made of 4 quarks. And at the LHC, we found particles made of 5 quarks. So these are called pentaquarks, and that was a completely new category. Now, incidentally, that's really how fantastic the data from the LHC are, in particular at LHCb, which is my favorite experiment, is you just look, you found something weird, and then you investigate further, and oh, fantastic, a pentaquark. The pentaquark was found, one of the very first person who saw that there was something weird in the data was a summer student of mine who was working with me in 2013. He was looking at the data, and one of the modes he was looking at didn't make sense, because you could. Then it took us another 2 years to understand that this was due to pentaquarks and to prove it, but the signs of it, they were already there.
Yeah, this is very interesting, because this really points to something that happens here at CERN all the time, that we love it when things are broken. When something pops up. It's very rare to have eureka. I don't think I've ever heard somebody at CERN running around going eureka, but you often hear, this is strange. Yeah. I don't understand. This is something I don't understand.
This is weird.
This is weird.
That's the CERN version of eureka.
Yeah, that's CERN and physics in general, because in good science, we doubt our results all the time. We're not sure about our results. As experimentalists, I think theorists are always sure about their results. But experimentalists, we doubt them, and we ask our colleagues to take a look, and then we ask other experiments to take a look. And in this case, you guys have come up with a lot of really nice, strange moments, things that weren't expected. I remember that, the pentaquarks coming out, tetraquarks. I've even heard there's searches for 6 quarks together. I've heard them called hexaquarks, but then someone told me there's also this possibility of something called a sexaquark.
Yeah, the hexaquark is the general name, and then there are a few special cases, trademarks that were invented by one particular theorist who liked to give another name. So sexaquarks, that's a potential dark matter candidate with 2 up, 2 down. These are the light quarks that you find in the proton. Then one strange quark, that's the third one. And they would be so tightly bound together that they wouldn't interact with anything. So this could be one of these particles that explains why there's only 1/4 of the matter in the universe that we see, and the 3/4 is invisible. And it could be that. It could be another new particle, but that's one of the candidates. And if that particle exists, it's very likely that we can produce it at the LHC. So we are looking.
But can we see it? Will we see it?
Well, what we will likely not see it. What we will see is that something is missing.
Okay.
So there are 6 quarks missing that went away, that didn't interact with anything, and so that are kind of missing in our count of particles.
Okay, that would be amazing. And to see things like this, which I guess would be very rare, you need a lot more data. And so the LHC has, I believe, 1, maybe 2, we'll see. It depends on how decisions are made. Years left in what we call Run 3, which right now apparently is going extremely well. I think by the end of the week, at least for the Atlas experiment, which I belong to, we will have taken as much data as we did in any other year, which is really, really great. We love data, good data. And after that, though, Atlas, we're going to tear apart. And we're going to spend 3 years, and I think this is true for other experiments as well. I know it's true for CMS. We're going to tear the thing apart and revamp it in order to be able to handle a much higher rate of collisions. And our friends at the LHC are magicians because they give us amazing beams. They're going to be revamping and giving us many more collisions per second, high-luminosity LHC, and which will give us a chance to look for these very, very rare things like dark matter. In other possibilities are just simply that it's an elementary particle. We have no idea what it is, right? We are clueless. We know there's stuff out there. We've mapped it out in space. Vera Rubin measured the spin of stars and galaxies, and we simply don't know what's the stuff that's out there that only seems to interact through gravity. And so we're hoping, that's one of the things we hope for. We also hope to have very strange things come up that we don't expect. I was going to say, I watched the beginning of 3-Body Problem. Did you guys watch that at all?
Yes.
3-Body Problem. And I love the show. It's a good show. I recommend it. But I hated the scene in the first episode where they were all saying physics is broken, because that's what we want. we love it. That's how we go forward, is we find out that the stuff we've measured does not agree with what we expected, and it means that we have to advance our theory because of stuff like dark matter. It's not in our model, our standard model of physics. So we're going to be going up. So I'm curious. I know the Atlas will be torn apart. What's going to happen to LHCb in the upgrade and for these 3 years?
So I guess LHCb, we've already done the how did you say, torn apart? We've already done that part, because during the path shutdown, we already kind of deployed our first upgrade. So this was kind of very intense years for us, because you take out really, like you say, all of your precious detectors with which you've done a lot of beautiful physics. And we have already upgraded most of it, all the tracking system that allows to measure, the information about the momenta and the vertices of the particles and so on. All of these have been changed. We've also changed everything that has to do with the readouts. We've changed the way that the trigger system, which is the system that allows you to reconstruct and record the data, to say it simply. All of this has been rethought and changed. So all of this is why the start of Run 3 was so important for us, because it was a whole new experiment.
Oh, okay. So you get like a 3 years off then, right? Well, we're
Yes, no, unfortunately.
We never have time off.
There's no time off. There'll be a lot of data to analyze. There'll be some smaller upgrades, which are also foreseen in the pipeline. And also thinking ahead of the future, there's yet another upgrade which is being thought of and planned. So there's already R&D going in this direction. So we have plenty to do.
And you have a special detector. I have to say, I've visited all the detectors on the LHC, which is great, and everybody is welcome to come here and to visit them. You can actually go underground, but only in the winter when there's no beam. You don't want to be down there when there's beam. And they're all beautiful. All the experiments are beautiful. But really, LHCb stands out. It's not like the others. The others are symmetric. They're like a cylinder built around the collision point, so they capture everything that comes out, and they can reconstruct the entire event, we call it, when there's a collision. Why is LHCb different? And tell me about that.
So the reason we're different is physics and money. Physics is because when you're colliding particles, the heavy stuff, like the Higgs boson, is going to go in all possible directions. So if you want to catch as many as you can, you're going to cover the whole region around the interaction point. So ideally, you'll build a sphere, but that's difficult. So practically, you build a cylinder. That's what ATLAS and CMS look like, and that's also what the previous experiments at the previous accelerator look like. Now, we are looking for B quarks, and B quarks are relatively light compared to the energy that is available in the LHC. And the light stuff tends to stay close to the beam. So it goes forward or backward. It goes in both directions. So when you're looking for the light stuff, you want to cover this region. There are also going to be B quarks that are going to go up the roof. But then it would be very expensive to actually cover all this region where you wouldn't see a lot of B quarks. And it's rather interesting to cover the forward region. Now, ideally, that means that you do a detector that looks like a bow tie, which covers both sides. But when we started the LHCb experiment, one thing that CERN told us immediately is, this is your cavern, you'll have to fit in here. That was the cavern of Delphi, the experiment that was running at the previous accelerator lab. And it's 20 meters long. So we could have done an experiment with a collision point in the middle and then two 10-meter long detectors on either side. But we found out that it was more optimal to actually have the collision in one side of the cavern and then a bigger detector on the other side. That means that half of the B quarks, those that are going what we call in the backward region, well, we don't see them, but we're still collecting a lot.
Okay. So we have a question from Chetna, our director.
My Dutch colleague Ron is asking, do we have a bicycle in LHCb experiments? Something really popular.
Of course, someone from the Netherlands is going to ask that question. Why is there a bicycle at the beginning of your experiment?
An experiment is built from several elements that are each specialized in doing one particular thing. And the very first thing is to try to find out the position of the proton collision as precisely as possible. And then there is this B quark that flies and decays to other things. And we also want to know as precisely as possible where that happens. These things, these collisions and the decay, we call them vertices. That's a vertex, and we want to find their location as precisely as possible. So we called that the experiments the vertex locator, or in short, the velo.
The velo.
And of course, it was a Dutch person who came up with that name.
With the name velo? Because that's French to me. Is it also
Yeah,
Dutch?
I don't know. Velo is universal, but it's clear it's the French word.
It's a French word
It's a
for
French
bicycle.
word
So
for
now
bicycle. It comes from velocipede. It's a veloci is fast. It's the fast way of walking. That was the original name for a bicycle in French.
Oh, now I've learned something new as well. So thanks for asking that question, Ron. So the velo. Okay, now I understand why velo is called a velo. I got to ride my velo into work today, and it was fun. It was very nice. I want to just go a little bit more on the physics as well, because we mentioned that we're going to go to higher luminosity anyway, and you're going to be getting a lot more data. The things that you are studying, now you're studying this sort of asymmetry, the CP violation. You do this, there are several different kinds of interactions that we can measure. We can do electromagnetic, and weak interactions, strong nuclear interactions. Gravity, well, we don't really have a chance at it. It's far too weak. What do you focus on in LHCb?
We have actually a very broad program, and it's one of these things that we're very proud of. So like you say, we have CP violation. Then there is another aspect that we're very interested in, which are called rare decays. The reason we love these is that, as their name suggests, they happen very rarely. And they can be a super cool probe to look for new physics. So I don't know if you've discussed this in a previous program, but
We always look for new physics.
oh, exactly. So new physics is all of this physics that we need, which is beyond the standard model, anything that is not described within the standard model. So these family of rare decays, they're very cool because the way that it works is that you study some of their properties, which can be well predicted in the standard model, and then you compare that with what you're measuring. And then you see if you have an agreement between your data and what the standard model predicts. Because these processes, you can have these new particles, which we don't necessarily know, which could contribute to this.
Okay.
So this is one of the strengths of LHCb, is that we can search for new physics in an indirect way. While our friends at Atlas and CMS, they often look for new physics directly. So they will look for new signatures directly in the data. While here, we will do it a bit more in a contorted way. So this is one of the things that we would like to do.
Looking to see if it changes, maybe cross-section or different measurements that
Exactly.
you get.
Angles, branching fractions, all sorts of things.
Okay. And in the meantime, you're filling up that book with all sorts of different hadrons, different combinations of quarks. And that's interesting, too, because that's really quantum chromodynamics, right? The strong interaction that you're measuring there from many different angles, I guess.
Exactly, yeah.
Very good, very good. Maybe we can ask you simply about the future. My understanding, I think this is a good approximation, the LHC has only actually given us about 5% of the collisions that it's going to give us in the long term. So probably, maybe if you're leapfrogging us, not this next shutdown, but the one after that, you'll probably make some big changes. So we're going to get a lot more data. Are there big plans? Are you already working on things for these different upgrades for LHCb?
We're working on the next upgrade with a completely new detector that will still have the same shape roughly, but with detectors that are going to be more precise, and that will include timing, because we want to know not only where the particles went through, the ones that traverse the detector, but also at which time, which then will allow us to know exactly from which proton-proton collision they came from. We'll have so many in the velo that we will not be able to tell them apart without this additional information. So we will need to do this. To do all our analysis in 4 dimensions, the 3 spatial dimensions plus time. So this is a big program for everybody who is doing detector developments, because they will have to add this information and as precisely as possible. And the the goal is to gain in precision, because when we have more data, that means that we can measure the tiny differences between matter and antimatter more precisely and challenge the standard model up to a very high precision. But it's also the very rare stuff that is now too rare to be seen that will then first show up, so we can say we've seen it, and then we'll have plenty of these rare processes so that we can measure how frequent they are, and eventually we can even characterize their angular distributions and other properties, exactly as we've done for in the beginning of run one, where first we had to see things and then start to characterize it, and now we're doing precision measurements with rare decays, and there are many other rare decays that are so much rarer that we haven't seen them yet, but we'll do the same program with them and challenge the standard model even further.
Very good. I mean, it's one thing that's very interesting is there's a lot of amazing physics that's coming out that was not expected from the LHC experiments. A lot of this precision physics. Usually you do precision physics with E plus, E minus machines, because there you know exactly your energy, but we're getting that out of the LHC, and it's incredible. I think all of the experiments are finding much more than they had expected that they would find. We're often asked this question, at least on Atlas and CMS, what have you done since the Higgs boson? Yeah. A lot. thousands of papers have come out, and I'm sure the same is true for LHCb. LHCb and ALICE, which are the fourth experiment I hadn't mentioned yet here, are often considered the smaller collaborations on the LHC. Tell me, what is a small collaboration like on the LHC? How big is LHCb?
1,600 people.
1,600 people?
Yes.
That's a small collaboration.
Yeah. But in the case of LHCb, it did expand a lot in the last years. So I think that when I was a student or so, I think it was a bit closer to 1,000, and now it has expanded, and we have people we didn't have people from the US, for instance. Now we have people from the US, Australia, and we're kind of growing that way.
Well, people they see success and they get on board, right?
No, it's very cool. And the number of institute, I never know this number by heart.
It's now 100. We just crossed the 100.
I think yeah.
That's amazing. I mean, it's wonderful to see on all of these experiments is that you have people from all over the globe.
Absolutely.
Who join. You can look at the countries that are members of the experiments as one thing, and that's you probably have, I don't know how many you have on LHCb, but quite a few.
20-ish. It's not that many.
But if you look at the nationalities of the people, they come from the entire planet.
Yes.
And that's a really, really, really great thing. Yasmine Amhis is a research scientist at CNRS. That's the Centre Nucléaire pour Recherche...
National.
Oh, National. I knew I'd get it wrong. That's the Centre National pour Recherche Scientifique.
Very good.
Scientifique.
Perfect.
CNRS.
Yes.
Yeah. Okay. You thought that was hard. Now I have to do NICAF.
Good luck.
Yeah. Okay. So Patrick Koppenburg is a physicist at NICAF, and I have it written down so I can do it. The National Institut für Subatomophysica.
Yes.
How's that? Yes. Okay. I got the Dutch one, all right? I'm French, actually, but never mind. This has been Early Morning Coffee at CERN, a podcast by the scientists at CERN about the science of CERN. You can find all of our episodes on the CERN YouTube channel. Just look for Early Morning Coffee at CERN, or wherever you get your podcasts. And now that's everywhere. So we're on Spotify, Apple Podcast, CastBox, Deezer, iHeart, Geo 7. I never heard of that. I'm sure it's really, really good. Listen Notes, Player FM, and Podcast Addict. Anywhere you get your podcast, be sure to add us to that list, to like us, to share us, to do whatever you're supposed to do on social with us. Make sure your friends know about us. Our editor and producer is Chetna. Krishna. Joni Pham is our social correspondent. Our executive producer is Jacques Fichet. Ron Suykerbuyk, right over there, is our technical lead behind the camera. Our studio manager is Max Bryce. Sound design by Piotr. Traczyk. Our original theme comes from the Canettes Blues Band. Yay. Many thanks to Paolo Catapano for her advice on strategic planning, and a big thanks to the ECO team, that's Education, Communication, and Outreach team at CERN, for providing us with access to this beautiful Wire Chamber Studios, and all the help that comes along with it. The opinions expressed here are our own and do not necessarily reflect those of CERN or our colleagues, although I think they ought to. My name is Stephen Goldfarb, and this has been Early Morning Coffee at CERN. We'll see you next time. Take care.